Now that we know the basic structure of our IV curves, we can talk about a family of IV curves. And so what we can do is we can just select different values for our gate to source voltage, and we're going to see we have different magnitudes of our current. So we sort of looked at that for that small linear case, but of course that applies across the whole range of operation. And so what we see is that this looks very similar to what we saw for our bipolar junction transistors. So if we're assuming that this is for an enhancement mode device, then this bottom blue curve here is going to be for some VGS1, which is greater than our threshold voltage. And again, if it's enhancement mode, we're going to have that threshold voltage is positive. If it's depletion mode, then we can have negative gate voltages and still be turned on. So remember, our enhancement mode, which is what this is showing above, is going to be a normally off device, and we have to apply some voltage in order to turn the device on. So if you want to see a figure for depletion mode with what that looks like with our different gate voltage values, so that would be our threshold less than 0, then you can look on page 139 in the text, and there's a figure that shows that as well. So what we're saying then is we can increase our gate voltage, so maybe this is some gate voltage VGS2, which is greater than our VGS1, and then this is going to be VGS3, which is greater than our VGS2. And then up here we have our VGS4, which is greater than our VGS3. So keep in mind though that we're looking at sort of discrete instances. Of course there is a continuum of these curves because our gate value is a continuous value. So we could have any gate value that would give us a curve sort of in between VGS4 and VGS3, for instance. So another thing that we notice is we have this dashed line over here corresponding to our VDS sat. And so remember, our VDS sat was just equal to VGS minus VTN. So this is our gate voltage minus VTN. So that's why we see the value sort of shifting over to the right as our VGS is increasing. So we can mark these points on each of the curves that correspond to the different VDS sats. And so what we see is that for higher VGS, of course, we have a higher VDS sat. And so this sort of dashed line is actually separating our two main operating regions. So we have our third operation region, which is cutoff, and of course that's sort of our non-interesting case where we just have 0 current in the device for all of our VDS values. So we don't have any inversion layer at all. So that would be cutoff down there. So let's go ahead and label that. So that's cutoff. And sort of our two more interesting regions then are here to the left of our VDS and here to the right of our VDS. So VDS sat, I should say. And so as we said at the end of the previous video, to the right of our VDS sat, we call this our saturation region. And on the left side, there's actually several different names that you'll see. A couple that are used in the textbook is the non-saturation region. It's pretty easy to remember, so if it's either saturation or non-saturation. You'll also see this called the Triode Region. So Triode Region. And you'll also sometimes see it called the ohmic region because we have that linear relationship at first. So again, various different names, but one thing to note is that this is kind of backwards with how we defined our BJT regions. So remember, with our BJT, our saturation region was actually over here, and our forward active mode was over on the right side. And so for a refresher on that, you can look on page 307 or look back in the notes. But the key thing that I want you to keep in mind is that ultimately, the reason we call it saturation region for one device and it's on the other side comes down to the physical device structure and operation as we looked through in the previous videos. But just as a point to keep in your heads that you want to be careful, saturation region is sort of defined a little bit differently, whether we're talking about MOSFETs or BJTs.